Today we're going to see the topic called architecture of 8086. What is 8086? First, we need to know what is 8086 and what is the difference between 8086 and 8085. What is the difference is that 8085 is a 8-bit processor. It can handle 8-bit data at a time, and it has a 16-bit address. We all know that about 8085. What is the advancement in 8086 is that 8086 is a 16-bit processor, and we have to show the difference between the data and address. So it is a 16-bit processor, so that obviously the address won't be a 16-bit address, it will be a 20-bit address. So 8086 is a 16-bit processor, and 20-bit address it has. The architecture is splitted into two portions called as bus interface unit and execution unit. Bus interface unit is nothing but for data transferring from memory to the processor or input output device to the processor, for storing the data or sending the data to any outside device. That and all will be taken care by the bus interface unit, and doing this arithmetic operations or logical operation, all those things will be taken care by the execution unit. Already I told you that for getting a 20-bit address conversion mechanism is there in the architecture. First, we will see how the address of 20-bit is getting from 16-bit registers. Let us take two 16-bit address, which is there in segment address, which is called as segment address and offset address. That here I have mentioned um, 2000. 2000 is nothing but a 16-bit address, and similarly 0002 is nothing but another 16-bit address. If you do normal addition of this segment address is nothing but it may be a code segment or a data segment, and offset address, which will tell you the which will help us to get a 20-bit address, which will be added with the segment address, so that we will be getting the 20-bit address. uh, for example, what is segment address is, if you take a node, that means that totally five nodes are there. In that, if you are taking a third node, nothing but we are mentioning third node, nothing but it's a segment address. In that, which page you going to write, nothing but offset address. So that we have to mention which node you have to take, and in that which page you have to write, then only you can able to write something on that address. So which node is nothing but segment address, which page is nothing but offset address, then only we can write in that note. So here that 20-bit address is how they are framing is that if you do direct addition of the segment address and offset address, we will be getting again 20-bit address called as, sorry, again a 16-bit address called as 2002. So it is completely a wrong address due to normal addition. Actually, the address conversion mechanism in the architecture which will do this kind of addition, how means that segment address is nothing but 2000 will be shifted towards left side 4-bit. So that the last portion, that means that MSB portion will be sorry, LSB portion will be vacant. Similarly, I am not going to do anything with the offset address, which will be as it is. So now it is like the vacant portion which I have shown in the LSB of the segment address will be considered as 0000. So that 0000 will be added with 0010 of offset address, which will produce you 0010. Then remaining and all normal addition. Again, if you come to the MSB of segment address, which will be 0010, but here it is vacant in offset address, and here it is considered as 0000. Now if you add 0010 with 0000, you will be getting 20th bit. So totally if you add, if you see all those things, which will be considered as a 20-bit address called 20002. It's a 20-bit physical address. So this is how that 20-bit address in the 8086 is framed. Then come back to the architecture. Already we have seen what is the address conversion mechanism, how it is done to get a 20-bit physical address. Already I told you it consists of the bus interface unit consists of code segment, data segment, extra segment, and stack segment, and the purpose and all we have already seen. Also, it consists of instruction pointer. Instruction pointer is used to point the next instruction address what the assembler has to execute. It will point the next address of the instruction. Let us take LDA 4500 is the first line. Then this example is in 8085 program. 8086 program is different. For whoever familiar for 8085, for them this example you can take LDA 4500 and then move B comma A. That means that while executing that first line LDA 4500, the instruction pointer will point the address of the second line called MOV B comma A. And that execution unit contains the following 8-bit registers. 8-bit registers, following 8-bit register. Actually, that 8086 is having 16-bit registers, but that 16-bit registers and all splitted as two 8-bit registers. Actually, AX is nothing but 16-bit register, which is not, which is splitted as AH is having 8-bit and AL is having another 8-bit. Higher order AH, lower order AL. Similarly, BX is also a register which can carry 16-bit at a time. That is why 8086 is a 16-bit processor. All the registers are having 16-bit carrying ability. So BH and BL it is splitted, and CX also another register which will splitted as CH CL. Then DX is also splitted as DH and DL. Whereas the CX and DX is a special register. CX is used mainly for counting purpose. If you wanted to do some operation for n number of times, that n number of time value will be stored in CX register. Similarly, the DX is doing a special operation which can be used for some multiplication and division operation. Then uh, it also consists of stack pointer, base pointer, and the source index, destination index. Stack pointer already I told you, it will point the address of the where to jump from main program to sub program to main program. All those things will be mentioned in stack pointer. And base pointer is nothing but which will store the uh, address for a temporary purpose. It is almost similar to a stack pointer. Clear explanation of this will be explained in a separate program. And then source index, where you can use this for storing the input data. That is why it is mentioned as source index. And the answers and all, that means the result of any manipulation, addition, subtraction, or any manipulation that can be stored. Output data and all will be stored in the destination index. So source index is for input, destination index is for output. And already I told you it is a 16-bit processor, microprocessor, and it consists of 20-bit address line. So 2 power 20. So it can handle how much memory? Totally 1 MB memory of capacity it has. but 8085 it can handle only 2 power 16 of memory location only it can handle. And what are the address line? In 8085, we used to have 80 to 87 and A8 to A15. Here, 80 to 8015. So it consists of 16. So still remaining is 4. That will be available in A16 to A19. Similar to 8085, here also this 80 to 8015 will be splitted as address and data with the help of with the help of ALE signals. And few general specifications of 8086 is it can prefetch up to 6 instruction bytes. What is prefetching is nothing but pipelining. Most important topic called pipelining is possible in 8086. What is pipelining means? If you pass a 5 liter of water in single pipe, it will consider it will reach in 10 minutes from A to B distance. But if I use two different uh, same variety of pipe with parallel connection, same 5 liter if I pass, it will be splitted equally so that it can travel quicker than when it is using single pipe. That is why it is called as pipelining. It has a pipelining architecture in 8086. It is not available in 8085. What is with technical concept, how to explain as pipelining is nothing but um, in 8085 and all, it will take one instruction. First, it will do opcode fetch LDA 4500. What it will do? First, it will take that LDA, its opcode fetch, and then 4500 means it will do memory read and then memory read, like that. It will do one by one. It will do, and then it will execute. So when it is taking care of the first instruction, it won't worry about the second instruction. But in 8086, while executing the first instruction, it will start fetching the next instruction, and it will do opcode fetching of next instruction. That means the process of completion of a program is easy and quicker than 8085. So 8086 is having a pipeline architecture. Pipeline architecture is nothing but it will fetch the next instruction when it is executing the current instruction. At a time, it is doing a dual operation. That is why it is called as it is prefetching up to 6 instruction byte. 6 instruction byte means when it is executing a first instruction, next 6 instructions it can prefetch, and it can do what opcode fetching, and it can do what decoding, conversion of that assembly language into machine language. All those things it can do up to 6 instruction, but not only next instruction, up to 6 instruction bytes it can do while executing the first instruction. So it is a time reduction process. And it is also 40 pin IC, and it can hold it can work with 5-volt power supply. And already I told you, bus interface unit consists of code segment and data segment, and their use and all already I have mentioned. Also stack segment and instruction pointer. Already told you, instruction pointer points the address of next instruction to be executed. And a bus interface unit operation is nothing but generally I mentioned that bus interface unit can do fetching, and then writing data to the memory, and then write the data to the port. Port means input output device. Similarly, read data from the port, from the input output device you can do. Bus interface unit. So bus interface means it is used to interface either memory or any input output device. Execution unit, already told you, it will do all those ALU operations, nothing but arithmetic and logical operation. It will operate with 8-bit as well as 16-bit, because your AX register is splitted as AL and AH. Similarly, BX register is splitted as BH and BL. So you can do 8-bit operation as well as 16-bit operation. Already I told you this AX and all splitted as AH and AL. All those things already we have seen. And these topics also I have explained: stack pointer, base pointer, source index, destination index. And that registers of 8086 is split as general register, index register, pointer register, and flag register. Till now, we have not seen what are the flag registers available in 8086. Similar to 8085, few flag registers are available in 8086 also. That and all we will see elaborately in the next few slides. And segment registers also is there. Again, this general purpose registers, like already told you, AX is split as AH and AL. It can be used for multiplication and division and taking input and output. BX again, it can be used for what? Base address register. What is base address registers? That and all we will see later. And then CX already told you, it is used especially for counting purpose. And DX, it can be used as a normal register also, as well as it can be used for counting purpose. And DX is used for division and multiplication, as well as it can be used as a normal register. And source index register SI, where you can load the input data, and destination index is for loading the output data. Base pointer is used to access parameters passed via the stack. Already I told you base pointer is almost similar to the stack pointer. And then we know that a stack pointer, for what purpose we will be using. Then segment registers, code segment, data segment, extra segment, stack segment. It is separately given so that data won't disturb the code segment point, and code segment data and all will not be disturbing the data segment. So programmer won't get confusion, and the programs also can be executed successfully without any error, which these kind of error will happen in 8085. But due to the splitting of the memory location like code segment and data segments, all those things, the programmer won't get confused, and the program uh, can be successfully executed. Flag registers. Flag registers, already we know 5 flag registers in 8085 is there. In 8085, sign flag, carry flag, auxiliary carry flag, parity flag, zero flag, all those flags are there. Similarly, those flags are also available in 8086 as well. Here, various flags. OF means overflow flag, DF means direction flag, IF means interrupt flag, TF means trap flag, and then SF means sign flag. ZF is nothing but zero flag. AF is nothing but auxiliary carry flag. PF is nothing but parity flag. CF is nothing but a carry flag. In this, already we know that CF is carry flag. PF parity flag also we are familiar. AF also we are familiar. Auxiliary flag, and ZF is nothing but a zero flag, and SF is nothing but a sign flag. These are all already we are very much familiar. And TF is nothing but trap flag. Already we know that in the various interrupts, trap is having highest priority. Once that highest priority is getting enabled, this will become 1. Or if it is 1, the trap interrupt has arrived. So in order to mention, in order to run a program in a single execution without any interrupt, any other interrupt should not disturb the processor. For that, if I make this as 1, or if trap signal has came, this will be 1. So that's why the other signals and all will not be disturbed this. So it is having highest priority. So when the trap signal came, this will become 1. So this interrupt flag is nothing but you can enable or disable other interrupts. For that, interrupt flag will be used. Direction flag, with the example I will explain in the future coming slides. And overflow flag is nothing but if 16-bit register is getting overflow, that means the answer is more than 16-bit value, the overflow flag will be set, so that you can identify there will be a overflow of answer. Already told you, overflow flag is nothing but when you are doing addition or subtraction, overflow flag indicates that the result has exceeded the capacity of the machine. Already we know that a zero flag, when the answer becomes zero, it will be set. When the answer is negative, sign flag will be set. When the answer is having a even number of parity, it will be one. Odd number of parity, it will be reset. That means it will become 0. And trap flag, already told you, in a single step without any interruption, the instruction can be executed with the trap flag because it has highest priority. And interrupt flag, you can set or reset the other interrupts than trap flag. In set or reset means you can mask any disable the other interrupts, like few other interrupts and all maskable interrupt. When compared to trap, other interrupts and all maskable interrupt. When compared to the direction flag DF, let us consider memory location 1 and memory location 2. Memory location 1 starts with the address of 1000. Just for the example, I'm saying actually it should be a 20-bit address. Here I have mentioned with the 16-bit address. Actually, it should be a 20-bit address. Starts with 1000 to 2000. So memory location 1 starts with 1000 to 2000, and memory location 2 starts with 3000 to 4000. So when you wanted to transfer a data, a string of data, a bulk data from 1000 address to 2000, that means I'm incrementing the address 1000, 1001, 1002 like that. Incrementing the address from 1000 to 2000, these data which is available from 1000 to 2000 will be bulk transferred to the memory location 2 from 3000 to 4000. That means again what I'm doing, I'm incrementing the address from 3000 to 4000. Then for this purpose, the direction flag should be 0. That is why it is mentioned in the point C. When it is reset, the string bytes are accessed from lower memory address to higher memory address. Lower memory address means 1000 to 2000 and 3000 to 4000. So I'm incrementing the address from lower address to the higher address, and the data from 1000 to 2000 will be bulk transfer to 3000 to 4000. If in case if I wanted to transfer a data from 2000 to 1000, that means I'm decrementing the address 2000, 1999, 1998, 2000. These data 2000 to 1000, these data I wanted to transfer from 4000 to 3000 address, means I need to decrement the address. For that, the direction flag should be 1. If I wanted to increment the address, the direction flag should be 0. If I wanted to decrement the address, the direction flag should be 1. And then architecture of 8086 is over. Now we will see addressing modes of 8086. In addressing modes of 8086, there are different types of addressing mode. First one is register addressing mode. Here I have mentioned the instruction called move AX, BX. Move AX and BX. Both are AX and BX are two 16-bit registers. So this is I think you are familiar with addressing modes of 8085. There we will be mentioning move A comma B. Here instead of using A comma B, we will be using AX comma BX. AX is nothing but a 16-bit address. BX is nothing but another 16-bit address. So you can transfer a 16-bit data from one register to a 16-bit data of another register. BX content will be transferred to AX content. So here both are we are handling with register. That is why it is a register addressing. Then immediate addressing. Here immediate addressing is nothing but move ch comma 3a. This move 3 ch comma 3a is nothing but ch is a one part of the cx register, higher part of the cx register. Here we will not be using mva and all. For immediate addressing, move instruction only we will be using ch comma 3a. 3a means it's a value where you can store directly to the ch register. Then we will be using next addressing called direct addressing. Direct addressing is here the example given is move in bracket 1234 comma ax. In bracket if we are mentioning, it is a offset address. It has to be added with the segment address. Already I have explained with I have explained the address conversion mechanism. Their offset address is 0002. Here in the program they are given offset addresses 1234. Let us assume that segment address is 1000. So the 1000 has to be left shifted towards 4-bit, so that you will be getting 10,000. That is why for left shifting they have mentioned as DS. DS is nothing but data segment. Already I told you their segment address will be added with offset address. That segment address has to be left shifted 4-bit. For left shifting, I'll be multiplying with 10. If you have calculator with you, you can multiply 1000 with 10 hexadecimal number, so that you will be getting 10,000. So it is nothing but left shifting of 1000. That means left shifting of segment address. So you'll be getting 10,000 hexadecimal value that has to be added with offset address which is given in the instruction 1234. Now we will be getting 1 1 2 3 4. That means 1 1 2 3 4. Nothing but a 20-bit physical address we will be getting with the help of direct addressing. Why it is direct addressing means one of the address. That means that the offset address given directly in the instruction. That is why it is called as direct addressing. Then register indirect addressing. Register indirect addressing is nothing but in move here they have mentioned given an example that move bracket bx comma cl. Here they have not given the address directly in the instruction. They have given bracket of bx. That means bx is a register which has some value. That value we have to take, that will be added with that will be the offset address which is not given directly. In the previous example, third example, direct addressing, they have given the offset address. Here the offset address is given in bx register. We have to search the bx address, get the offset address. Again assume that your data segment address or segment address is nothing but 1000. The 1000 will be multiplied with 10h, so that you will be getting 10,000 h. Then bx content, assume bx content is 0300. Now the bx content I have entered into the register bx and I have got the value what is there in bx. That is why it is called as register indirect addressing. Again I am getting only 16-bit offset address from the bx, and then that has to be added with the segment address, so that I will be getting a 20-bit address. Here what address I am getting is 20-bit address is 10300. 10300. Nothing but it's a 20-bit address. Then the fifth subdivision of addressing mode, base index addressing. Base index addressing is nothing but source index. Here they are mentioned. So assume source index content is 0 200, and already I told you bx assume 0 300. Now what we have to do is that the bx content and si content, in the fifth example bx content and si directly will be added. So what I will get 0 300 plus 0 200, I will be getting 0 500. That 0 500 is a again 20 bit 16 bit address. This will be the offset address 0 300 plus 0 200 of si and bx. These two first I need to add. Bx is nothing but 0 300, si is nothing but 0 200. These two I will add, which I'll get, where I'll get 0 500 as offset address. That offset address I am going to add with the segment address. Already told you segment address is 1000. That will be multiplied with 10h, means I will be getting 10,000. That means it is indirectly I am getting left shifting of that 1000. So when I am doing left shifting of 1000 4 bit, I will be getting 10,000. These two will be added. That offset address of 0 500 with 10,000, I will be getting 500. Nothing but a 20 bit address I will be getting with the help of base index addressing. Then register relative addressing. Register relative addressing is why it is called as register relative addressing is register. Here what I am using is bx, and what is relative means I will be using a value, a constant value, which will be added, which will make me to get which will make me to get address of offset address. So bx content I have to go and check. Let us check. Already assumed that bx is 0 300. 4 is nothing but a relative value. So 0 300 plus 4, which I will get 0 304. This is my 0 304 is nothing but 16-bit offset address, and that assumed 1000 data segment address will be multiplied with 10 in order to get 4-bit left shift. So this 0 304 with 10,000, if I add, I will be getting a 20-bit physical address as 10304. So it is a 20-bit address I am getting. Then base relative index addressing. Base relative index addressing is again a 20-bit address we will be getting, like base bx I am using, and then bx value I will be getting, and then si value. So si value already I told you assumed as 0 200, and bx value is assumed as 0 300. These two will be added. Along with this I am going to add array value is 1000. So 1000 plus bx plus si, everything is 16-bit value only, so that I am getting a 16-bit offset address 1000 plus 300 plus 200, which I will be getting 1500. That 1500 is a 16-bit address which will be added with left shifted segment address, so that I will be getting 20-bit address. So these are all the various addressing modes of 8086. Thank you.